introduce and discuss some common time domain functions. You may have seen some of these. If you haven't, then there are some additional functions that are commonly used in electrical and computer engineering. They're often used to represent switches or to represent very fast pulses, and so that's what we'll introduce here. It'll be, once again, be important, particularly in this case for the Laplace transform units in the class. So common time domain functions. The first of these is the unit step function. The unit step function is a function that's defined as having a value of 0 for t less than 0 and 1 for t greater than or equal to 0. And it's denoted u of t. So it can be used to represent a switch or a spontaneous change in a signal or in a system that's turned on or off, for example, at t equals 0. As an example, the exponential decay function, e to the minus at, is basically an exponential that starts at t equals negative infinity. But in fact, we don't ever look at e to the minus alpha t for t less than infinity because it's always referred to as a causal signal. In other words, there's something that initiates or causes the signal to occur. And so in that case, we can describe it as e to the minus at times u of t. So one of the primary applications of the step function when it multiplies another function is to, quote, turn it on or switch it on at t equals 0. The unit step function can also be shifted, so in addition to u of t, you can have u of t minus tau defined, where tau is some delay, meaning that the step function would turn on at some later time. So here's an example of a function that's shown, and we're asked to describe it using the unit step. So the first thing we want to look at for this function is we want to look at the fact, first of all, that it's 0 for t less than 0, and it's 0 for t greater than 3. So we want to turn the system on at t equals 0, and then notice that there is a change at t equal 2. So what we would like to do is, first of all, we get some representation. I don't want to do that. I want to do a pin. First of all, we get a representation of what that initial sloped line is. So we need a function to describe this line. And then we say, okay, well, I want to start that at t equals 0 here. And then I want to turn it off at t equal 2. So that gives me this segment of this function that I want to represent. Next thing I need is an equation for this line, which is illustrated here. And then I want to turn that one on at 2 and off at 3. So the first thing I need to do is I need to get a function that represents the equation for the two lines. So if it's been a while since you have looked at slope, intersect, or point representations of how to write the equation for a straight line, that would be something good to review because we will be doing that in this class. So it's important for you to know how to write a straight line equation. For this first curve, the equation is just f of t is equal to t, or x of t is equal to t. For this second line, it's got a slope of negative 2, and I use similar triangles a lot in order to find y-intercepts. I just do it in my head geometrically. But you could realize that it has a slope of negative 2 and it passes through the point 3 and 0. And from the point slope formula, get the equation for the line. Or you could just realize that if I extrapolate this line on out, it's going to intersect the y-axis at a value of 6. Meaning if you write this as 2 times t minus 3, note that that would be minus 2t plus 6. So that would also represent that straight line. Now that line is going to need to be initiated at t equals 2 and turned off at t equals 3. That enables us to have a 0 value of the function on either side of the actual curve. So the signal illustrated in the figure can be broken up into two components. And the first component turns on at 0 and turns off at 2. And so the book refers to that as a gate pulse. That's fine. basically u of t looks like this. The shifted step function would be negative, and it is shifted to the right by the value 2, so it would look like that. And then if we take the difference of those, so actually it would be the sum, because I've already used the negative sign by representing this one. So if I take the sum of negative u of t minus 2 and u of t, then what I'll end up with is a green line that actually ends up being a square that then returns to 0, because at this point where t equals 2, I begin to pick up this other curve, which was 0 prior to 2. So it gives me this little square pulse that has a magnitude of 1 and turns on at 2, at 0, turns off at 2. So this is 0 here and here. So if I take this and I multiply it by the straight line, I will only get the portion of the line that exists from 0 to 2. So I take that first expression, t, or the line on the previous page, so that would be this one. So I take t and I window it by turning it on at 0 and turning it off at 2, hence giving me that little brief ramp that's shown. And finally, and this describes a little bit how to get the equation for that second line, I then take the second line, whose equation we determined was given here. It begins at 2, so I use a time-shifted step function at t equals 2, and then it turns off, quote-unquote, at 3, so I subtract a step function at 3. That then windows this function between 2 and 3. So the result of that is I've got this piece and I've got this piece, and I'm going to add the two of those together to get the total function. So this is an example of where the step function provides a windowing function. So here's what that looks like when you write it out longhand, and then you could of course do some simplification by combining these two terms. You've got a negative t and you've got a negative 2t, so you could combine those, which is how we got this middle term. And then finally you've got the t minus 3 term as well. So I want to look at something specifically. You see here we have a t minus 2 and then we have a u of t minus 2. Okay, what this represents is literally t minus 2, so it represents a line. This represents a switch. So while you can go in and do some mathematical, moving around of things, you could call it minus 3t plus 6. You could write it out as two terms. You could simplify it like they've shown here as a single term, multiplying the step function. The step function cannot be simplified. It can only be added with another step function with the same time shift. So what that means is you really need to treat this u of t minus 2 almost like it's a separate variable, q or p or whatever you want to call it. And same with this u of t minus 3. You can't come to the interior workings of the step function and change this 2, because that would change the definition of the problem. So if you have a step function u of t minus 2 and you need to do some kind of simplification, this is a shifted function of the variable t minus 2. So there's really no way to simplify that. That becomes sometimes a point of misunderstanding that I've observed in students. So you don't want to try to mess with the u of t minus 2. The other function of interest to discuss is the unit impulse function. So with the unit impulse function, it basically is denoted del of t. It represents a pulse that is infinitely short in duration and infinitely tall in magnitude. So it's equal to 0 everywhere except at t equals 0. And one of its properties is if we take the integral from minus infinity to infinity of the impulse function, we'll get 1. That just means it has an area of 1. Infinitely narrow, infinitely tall, but area of 1. So step functions could be weighted. If we had an a out here in front of this del of t, that would come out of the integral sign, and this integral would be equal to a. So impulse function under integration is 1. If it's got a constant, then it's just whatever the constant was. Now, the impulse function is approximated pretty often because it is kind of a mathematical concept to be infinitely tall and infinitely narrow. So a lot of times it can be represented, for example, as a rectangular pulse that has a very narrow width, where epsilon here is very small and has a height of 1 over epsilon. And you notice if you run it from minus epsilon over 2 to epsilon over 2, then that would give you a width of epsilon with a height of 1 over epsilon, which would give you an area of 1, which satisfies the definition of the impulse function under integration. Now, what happens is, as you let epsilon approach 0, then 1 over epsilon gets taller, and epsilon over 2 gets infinitely narrow, so you can, in the limit, achieve the impulse function. And there are other possible approximations for an impulse function. The triangle, the Gaussian, the exponential. Sometimes the exponential with an absolute value is used. Anyway, any of these approximations have been used for an impulse. Why would you choose one over the other? Typically it's for mathematical convenience and really no other reason. So an interesting property of the impulse function is that we take some function phi of t and we multiply it by del of t, then that basically ends up being phi at 0 times del of t, because del of t doesn't exist anywhere except at t equals 0. So since this is 0 everywhere, it selects whatever the function's value is at 0. Likewise, if you use a shifted impulse function, so what this would be is this would be an impulse function located here at t. So if you shift the impulse function, then what that does is that selects out, that's equal to the value phi of t times del of t minus t, big T. So it's selecting a strength at the value capital T. And so that leads to an important property known as the sampling property, also known as the sifting property of the impulse function. So if we have an integral, and in this integral shown, del of t minus capital T is the impulse function shifted and located at capital T, phi of t is any function. So under integration, what happens is that phi of t is evaluated only at this one point, big T, and is no longer a function of time. Del of t is the impulse function integrated from negative infinity to infinity, and of course we know that that is equal to 1. So what happens under integration of an impulse, of a shifted impulse function multiplied by any other function, is we select the value of that function at t, and that's actually the value of the integral. So what the integration does is it gets rid of that impulse function that we saw on the previous page. This is pretty important in signal processing because basically this allows you ultimately to explain and represent mathematically what goes on when you sample a function. So everything from going from a continuous signal to a discrete signal, from selecting and weighting certain values, this allows you to get a mathematical representation of. So it ends up being very important. I will say that on my first exams, I almost always have an integral involving the impulse function just like this that is trivial to evaluate if you have learned what the sifting property is and how to evaluate it. Another useful thing is that if you integrate from negative infinity to t, so if you have a definite integral of the impulse function del of tau d tau, you end up getting the step function. So under integration, the impulse function produces the step. Hence, in converse, the impulse function is basically the time derivative of the step function. So impulse function and step function, both very important functions, used a lot to represent things mathematically. The exponential function is another common function. In this case, we're going to represent it as e to the st, where s is known as a complex frequency, sigma plus j omega in general. So you have e to the sigma plus j omega times t. The sigma part represents like a time constant, an exponential decay or growth rate. The j omega part represents oscillation with frequency omega. So this function e to the st, depending on the relative values of sigma and omega and whether they are negative or positive, can represent exponential growth, exponential decay, a constant, a sinusoid, a damped sinusoid. Right there, we've covered most of the functions that you see on a regular basis in electrical engineering. So here's a little bit of a discussion of that. And you can see that using this, you can then apply to the e to the j omega t. You can apply Euler's relation. You can also take the complex conjugate of e to the st, so you get sigma minus j omega t. From that, you can prove that this expression can be broken down as shown. So e to the sigma t cosine omega t can actually be written as 1/2 of e to the st plus e to the s star t. Kind of a useful property. I don't use this one a whole lot, but it does kind of mirror Euler's expression, Euler's relation, and give you a little bit of a relationship between this and what we did in the introductory material. And in fact, that's what they say right here. A comparison with Euler's formula, e to the st is just a generalization of e to the j omega t, where j omega goes from being just a frequency only value to, as I said, what we refer to as a complex frequency. In this list here, the author is basically going over the fact that you can use this to represent a constant, exponential growth or decay, sinusoid, or exponentially varying sinusoid, and what the variables s and omega would have to be to get each one of these. So I'm trying to stop as I go through these lectures and tell you, amongst all this mathematics, what is key. This is a key point. So what we've seen in this lecture, we've seen how to represent functions with step functions, which is important. We've seen the shifting property of the impulse function, and now we're seeing this, the fact that this generalized e to the st, where s is equal to sigma plus j omega, can be used to represent a number of different types of commonly occurring functions. And these are illustrated in figure 121. So here you're shown some of the different possibilities. A, B, C, and D relate back to these. They're not one for one, because what you have here is your sinusoid where sigma is 0. Here's your exponential growth, your exponential decay. No sinusoidal oscillation because omega is equal to 0. If they're both equal to 0, the line is flat. Here is an exponentially damped sinusoid, and here is an exponential growth sinusoid. Both of these would be cosine function because they're centered, they peak at the origin at t equals 0. We call both sine and cosine sinusoids. It's a very common expression. When you hear sinusoid, it typically refers to the cosine of omega t plus v. So damped and exponentially growing sinusoids. This one, in electrical and computer engineering, is relatively unphysical. You cannot sustain exponential growth in a physical system, in any physical system really. There are some biological and It's kind of bio-type situations where you do have exponential growth, bacteria growth, and other similar kinds of physical situations. But even that is not sustainable, because if you're growing bacteria, eventually they run out of food and they begin to die. So exponential growth is typically an unphysical solution, and if you get a solution that has exponential growth, you know that you either have a bad design or you somehow messed up in your math, because that's not really a physically realizable system. So this guy is not a very clear figure. I couldn't figure out what the guy was doing. I think what we're trying to do is we're trying to show that you have, if you go along the real axis and you go in the positive direction, this is the complex plane. As sigma gets larger and larger, you have exponentially increasing signals. Sigma goes less than 0, you have exponentially decreasing signals. On the real axis, you have no oscillation. As you deviate and depart from the real axis, then with omega not being 0, then you have oscillation. The right-hand side of the complex plane, because it is an exponentially increasing signal, is considered unstable. So if you want stability in your signal or system, you need to be represented on the left-hand side of the complex plane, and we will talk about that a little bit more. That's mainly a feedback and controls issue. We'll talk about it a little bit when we talk about systems. Okay, at this point, we want to make a final definition of how we look at things in the time domain, and we want to look at even and odd functions and the definition of even and odd functions. So a function f of t is said to be an even function if it is symmetric about the vertical axis. That would mean that x of t is equal to x of minus t. So you can flip it around the y-axis or the x of t axis, and you'll get the same, flip it around the vertical axis, you'll get the same function. It's like a mirror image. Odd functions have a different kind of symmetry. In that case, they're both flipped, and then the negative side is inverted. So an odd function, x odd of t, is minus x odd of minus t. So this flips and inverts on the negative side. So let's look at an example of even and odd functions. Okay, sorry, I guess I have one coming up. There are some properties. I'll give you an example. The cosine function is an even function, and the sine function is an odd function. So hopefully you can visualize those, and I'm sure I have a figure coming up. You can show that an even function times an odd function is equal to an odd function, that two odd functions together are equal to even, and even times even is equal to even. I should point out here that a function does not necessarily have to be even or odd. You can have functions that are neither, and that is not uncommon. Most functions, many functions, are neither. So you do not always have to have an even or odd function. Okay, here's my example. You can see the top figure, figure A. This is an example of an even function. Figure B is an example of an odd function. So because of symmetry around even and odd functions, this has some implications for integration. It means that if you have an even function and you're integrating from minus a to a, you can represent that as 2 times the integral from 0 to a. This simplifies work quite a bit in some of our situations that will come up, especially in Fourier analysis, because in Fourier you tend to have negative time. So being able to make this substitution a lot of times takes away at least half the work. For an odd function, if you integrate from minus a to a, you will end up getting 0, because the left-hand side of the axis will be the negative of the right-hand side of the axis, and they'll be mirrored and flipped. So you will not get a result there. Now, an interesting thing is, it does turn out that you can break down any signal as a sum of an even component and an odd component. So you remember I told you that not every signal is even or odd. Some signals are neither. So for those signals, it is possible to break it down into even and odd. And the way you do that is if you want to represent any arbitrary x of t as the sum of an even and odd function, you take the even part, which is 1/2 of x of t plus x of minus t, and you add that to the odd part, which is 1/2 of x of t minus x of minus t. You can show that as you add these two together, these two would cancel out if you simplify this, and you get x of t back. But by expressing it as these two terms, you can get an even part and an odd part. Is that useful? It can be. It can sometimes be useful. So that may be something that ends up being a useful thing to do from a signal processing perspective. So here's an example of how to find the even and odd components of a signal. So we have this x of t is e to the minus at u of t. And so what we want to do is we want to express it as a sum of even and odd. So to find our even, we take 1/2 of x of t plus x of minus t. So you can see this is our original x of t, and this is what happens when we change t to negative t. So we get this expression. Likewise, we can find the odd part by taking the difference instead of the sum, and that'll give us the odd component. So we have both even and odd components. Here is the original function. Here is the even part, and here is the odd part graphed out for you. So finding even and odd components of a signal, possible to do, not incredibly hard. As I said, sometimes useful, sometimes not so much, just depends on your application. Now, if you have complex signals, and we will work some in this class with complex signals, the definition gets a little bit different. So what you talk about in even and odd transitions to talking about conjugate symmetries. So a signal is conjugate symmetric if x of t and the complex conjugate x star of minus t are equal. And it is conjugate asymmetric if there is a negative sign inserted in front of x conjugate. So conjugate asymmetric signal is odd in the real part and even in the imaginary part. A real conjugate antisymmetric. A real conjugate symmetric signal is an even part and it's odd in the imaginary part, and a conjugate antisymmetric signal is odd in the real part and even in the imaginary part. Okay, I'm not going to emphasize or overemphasize the complex signal even and odd. If we need it when we get to complex Fourier series, we will review it then, but at this point, as far as the conjugate symmetry, that's not a big point of emphasis in this chapter, in this material. However, even and odd, being able to recognize what is even and what is odd, and being able to decompose the signal into its even and odd components is something that you are expected to learn and know. And the definitions of what is even and what is odd is something that you should commit to memory. Okay, that concludes the introductory part of the course for signals. In the next set of lectures, we will talk a little bit about systems. We're going to talk only briefly about systems because we want to move into looking at signals in the time domain and then looking at signals from a Fourier perspective. When we get to Laplace, we will come back and revisit the concept of a system, because then things like a transfer function become really much more relevant. So in the next lecture, we will do a brief discussion of signals and how they're characterized, but I'll put some of that on hold until later in the semester because I want to stick with this idea of early in the class, we are working primarily with signals. Okay, so that concludes the part of the lecture on signals and should conclude most of the material, with the exception of the last lecture for what's currently being discussed and tested in the class.